आइए हम सुने विज्ञान की अनकही कहानियाँ। आइए हम सुने विज्ञान की अनसुनी कहानियाँ। एक नई दुनिया की आवाज आपकी आवाज, विज्ञान की आवाज, की आवाज।
Celebrating Azadi Ka Amrit Mahotsav, we bring you a podcast series on STEM popularization, science, technology, engineering, mathematics and medicine, supported and catalyzed by the National Council for Science and Technology Communication, Government of India. This program is produced by Media for Community Foundation. Creative content and technical support is given by Purvasha Banerjee and Shushanto Das.
एक नई दुनिया की आवाज आपकी आवाज, विज्ञान की आवाज, की आवाज, की आवाज।
Vigyan Ki Awaaz podcast series aims to popularize new ideas of science and technology, which highlight STEM, science, technology, engineering, mathematics, and medicine. This brings to the surface the efforts and researches of Indian scientists, which is desired to bring a change in community learning and teaching, access to knowledge of resources, and social paradigms. Our goal is to spread the name of indigenous Indian research stories and their masters among the masses of society in a very easy manner. Bose Institute was set up in 1917 by Sir Jagadish Chandra Bose, the founder of modern science in the Indian subcontinent. It is Asia's first modern research center devoted to interdisciplinary research and bears a century-old tradition. The institute was founded as not merely a laboratory but a temple, with its principal aims being the advancement of science and diffusion of knowledge. Swami Vivekananda, Sister Nivedita, whose influence is reflected in the institute's emblem of Vajra, was significant in the setting up of the institute, and Rabindranath Tagore were among those who had consistently inspired and supported Jagadish Chandra Bose in his endeavors. Ever since the establishment of the Department of Science and Technology, Government of India in May 1971, Bose Institute has been an autonomous grant-in-aid institution of DST. Over the last century, the institute has endlessly strived to preserve the legacy of its illustrious founder. We welcome Professor Nirmalya from Bose Institute, who is an assistant professor in the Department of Biological Sciences there. We get an insider's perspective to his life and work in this podcast.
I'm Nirmalya and I'm assistant professor at Bose Institute. I have joined last year and the Department of Biological Science, and I work with cancers. So coming to my education, I have done my MScs from Department of Biochemistry, Banaras Hindu University, and then I did a PhD in National Institute of Immunology. And after doing my PhD, I moved to the US to do 2 postdoctoral research experience. One in George Washington University and another is in National Cancer Institute, NIH, USA. So from there, while coming back to India, I wrote a project on Ramalingasamy proposal from DBT, and I got a chance to work on prostate cancers. So I moved back to India and started working on castration-resistant prostate cancer. So normally, elderly males are affected in India with prostate cancer. Now, the problem is so this is also a disease of the hormones. So basically androgen, the male hormone, it is promoting prostate cancer in males. So clinicians try to interfere with the androgen metabolism, androgen synthesis, and basically they try to chemically castrate the patient, so using some kind of anti-androgen therapy. So I started working on that, and I found out that even after giving androgen therapies for first 2 years, the patient develops some kind of androgen independent growth mechanism for the cancer. So even when you give this therapy, it doesn't work. So then comes this terminology, castration resistance prostate cancer. So even after giving anti-androgen therapy, the patient do not respond. So I started working on that field when I came back to India.
Professor explains in detail about the steps and findings of his work.
What we try to do in our lab is try to understand the molecular mechanism of this androgen resistance. So we have different types of cells. In one where there is androgen positivity, that is when you give a drug which blocks androgen, these cells are killed. In the other, which reflects more the castration resistance phenomena, where they don't have the receptors for androgen acceptance, and so we use those cells to model our studies. So here we saw protein, a transcription factor which has DNA binding ability. Again, so this is known as ERG, the R group of proteins. So this ERG protein can form a fusion gene with another gene promoter, and normally they are not harmful, but once they form this gene fusion, it becomes an abnormal mutation in the cell, and then they start triggering what you call is androgen synthesis. So even if you remove the prostate by dissection or in the clinic by operation, still these cells which house the ERG gene can synthesize their own androgen, and this androgen hormone is again fueling the prostate cancer growth. So we thought like, why ERG protein is doing that? So we started using what you call metabolic stress to see how ERG is behaving in case of metabolic stress. Now why we use metabolic stress? So once a tumor grows, as I have told previously, so when a tumor grows, the core of the tumor do not get enough nutrients. So due to that, the core of the tumor is always under stress. So outside cells, when you put a therapy, the outside cells of the tumor will get killed, but the inside cells are still living. So once you remove the drug, these cells starts growing. Sometimes we call them as cancer stem cells and all. So ERG is helping to get benefit during this stress. So we found out last year while working with this stress, we found out that there was a coactivator which actually helps ERG in its functions during this glucose stress or say metabolic stress. So we remove glucose from the cells or we remove glucose from the mouse tumors, and we found out that in the normal situation where there is ERG, the tumors still grow. But when we start blocking the ERG mechanism, or when we start removing the coactivator from it using some chemical, we found out that the tumors decrease in this mouse under glucose stress. So we starved those tumors bearing mouse, and we found that out. We also saw in the patients, like we have a lot of data from patients where we saw that there are 4 different genes that ERG can activate during this glucose stress. So those genes are peculiarly antioxidant genes. So basically when you stress the cells, there is oxidation going on in the cells, and so cancer cells are having a high metabolic rate. Once the oxidation starts, so they will die. So to remove those oxidized radicals, the free radicals in the cell, it has to work in an antioxidant gene activation. So ERG helps in providing these antioxidant functions to the cells. So this is what we found out. We published it in Nature journal last year, and this story was covered by DBT also, and a lot of my peers actually found it very interesting and wanted to collaborate after that.
We thank Professor Shen for sharing his knowledge with us.